Okay, we'll try this again. The life cam gets pretty warm. It's a little worrying. So for the power supply, it feels a little bit like a case of mincing words, but I realized primary power is never the battery. So I need to find a way to really control anything. I mean, an offline supply, a UPS, maybe a generator, you want some kind of protocol to manage that. And so at face value, what this means is you take an offline supply, an AC to DC converter. You end up putting, can't see my eyes, can you? You end up putting it on, and sorry, you've got the AC to DC converter. You end up putting a current sensor on it, after it. Like, you just buy it as a unit. And that's certainly the easiest way. You could retrofit an existing system like that. But one of the key points is in all but the cheapest offline supplies, there's 2 points where it's already monitoring current. There's the power factor correction stage where you're taking, you're rectifying it, and you are switching in a capacitive load to make up for the fact that the load you're driving, which is a DC to DC converter, is inductive. And so if you had a building full of unpower factor corrected power supplies, it would look like a big inductive load because you have a transformer, you're pulsing current through it to get the voltage on the other side to be a specific value. So there's a couple different configurations. The more advanced ones that save you more power. I mean, even on the cheapest one, which is a single switch in between line and neutral, in that one you rectify it. You have the single switch between line and neutral. You are still reading the voltage, I'm pretty sure, because you need to control for EMI and you need to control for the power factor. So the feedback that you get, I said that backwards. You're controlling for power factor. You also need to control for EMI. And doing either of those things, you are basically metering how much power you let into the system. So right there, I mean, you get that information. The second one is on the DC to DC side. So after the power factor stage, you're left with about 400 volts, which is an interesting number because that 400 volts shows up in a lot of places. It seems to be a cutoff, minor tangent, it seems to be a cutoff for a lot of processes. I don't know if that's something inherent to the process. Guessing right now, they just tune the process so that you get a cutoff around 400, 600, because when you manipulate these values, you end up, because another cutoff is like 1200, right? So you start manipulating line voltage from 120 or 220, you get like 400 or 600. That ends up being a good value for doing magnetic torque calculations in motors. Those battery packs in Teslas, I'm pretty sure, are about 400 to 600 volts. And I mean, that's not just if they wanted to put it higher because it was a good idea to do that and buy better power electronics, they would certainly do so. But into that tangent. So PFC stage, the DC to DC stage is a little easier. I mean, you don't necessarily get directly current from the information that you see as you're controlling for voltage on the other side. But by monitoring the time everything is on, you are getting power. And that's typically what you want directly. You could, I'd have to go look at a circuit again, but you could turn that into voltage and current. At minimum, you would just need an ADC and a resistor somewhere to get voltage, and then you would know current if you knew power. So that's kind of the justification for that. I had this other project where I was going to build power supply. I need to get on that. I got caught up with doing it the right way the first time when I should do it iteratively. You can kind of see the progression as they go from less efficient to more efficient designs progressively. Part of the, just to give you some taste of that, part of the initial issue with just using a rectifier and then a single switch. So, you know, you have rectifier over here, comes in, you switch it to neutral. Um, the issue with that is each of those diodes, you get two diodes in a row. And your voltage drop from that is a couple percent of the overall efficiency. So when you're going for like 90+% efficiency, if you just naively make one, you're going to get 80 plus. So that 80 plus qualification is massively easy to get. A lot of those Energy Star green power supply things, as far as I can tell, they were mostly to get people to transition away from those old analog linear supplies where you have, they're not horribly efficient. They're like 70% efficient, I think. 50 to 70. The old style where you have a big transformer which takes the 120 volts AC down to like 60 hertz, 12 volts, or 60 hertz, you know, like 12.3 volts. And then you use an LDO. They didn't necessarily have LDOs when they were doing this, but you would use an LDO or just a linear regulator to take that 12.5, 12.3 down to 12. And then you would probably have a secondary transformer here for your 5 and 3. And you do some silicon stuff for the -12. That brings about some other directions I wanted to take this, where you just have 12. That's apparently a server specification. I did those other videos on those HPs, you know, about that big, and not as big as my head. And yeah, all those output is 12, right? I mean, if I want something else, I can make it on the board. Yeah, so I mean, it's one of those things that's not super interesting, but it will produce open hardware. Man, I need a haircut. That looks low-key awful. Man, what's up with that? Eh. So